Request from the audience to thank you, Nava. I had a request from the audience to go over the solution for this template just to reinforce what is going on here, because I only did a few rows and then we quit. I actually have the solution on the next template over, so I can actually show you, just click over and show you the solution on the next template. And so this is that page finished, at least run many rows. And so we got to about here. We got to about here. And, or maybe we got to about right about here. But as you follow this chain down at each row, we process the arrival. We figure out when the next arrival is going to be based on the random number we drew from the table. Mark that in the calendar. Roll down the next departure from the system here. This is the occupant of the system at this point in time. This occupant's going to depart. This particular random number sequence and this particular level of demand does not generate a lot of queue activity. There is not a lot of queue activity for this particular example. If I were to run this model longer, I might generate some more queue activity further down. Or if I were to increase the service time. If I were to increase the service time to maybe 3.5, this is, I believe, well, that's uniform 1 to 6, so these are on average 3.5 time units between arrival. So if I were to even just boost this up a little bit, just boost it up to 3.25 or something like that, we would start to see some queue accumulation. It's just we're in a stroke of luck here that the number stream is giving us a pretty easy ride in this sequence right here. We're not getting a lot of queue activity. There's a tab down below that says another example. I can pop over there and show you another example. This one is one where I'm using a different set of distributions. This is a uniform distribution for the service and the arrival, and I'm running these numbers down and doing the same kind of event calendar and queue structure. I don't know if I have got, this one's a little too messy to look at. You're not going to like that one. But regardless, the idea being that we have a particular event that has been processed from this event calendar, and that event triggers other events. That event triggers other events. Train stops at a red signal. In a signaling system, that might trigger other signals to change behind it or in other areas of the line. Train moves forward and occupies a train block. That's going to cause triggers and cause other signals in the system to change their indication. And when those signals change their indication, maybe it's going to cause other trains to stop in other positions. And all of those things are going to have to be marked in the event calendar as things that need to be processed next. So the next thing that might need to be processed is to get the train out of the block and then change the signal. That's an event. And then initiate the movement of the other train. That's an event. All these events would be queued up in the event calendar and be processed. And then we would have databases keeping track of things like how many things are in the queue, how many trains are queued up on the platforms at the station, how many trains are waiting at the hump yard to go over the hump and be classified. A couple other conversations I had during the coffee break that I think kind of share with, actually I'm kind of just doing the next slide in the presentation set right here. But some of the things we're interested in managing these systems in simulation is, I already mentioned variance reduction, but we're interested in reduction of variance. So we generate lots of runs of the simulation model, and we want to be able to see the solution of our model have some kind of cohesive answer. And we want to reduce the variance in our answer. The more variance there is in our answer, the harder it is to tell whether there's a difference between the two models. Let me give you an example of what I'm talking about. I have model A, and I run model A like, I don't know, 25 replications. A replication is a separate run of the model with its own set of random numbers pulled for the purpose of the simulation. So 25 replications is 25 runs of the model from the beginning with completely new sets of random numbers. And those 25 replications, let's say, give me some kind of output measure over time of the simulation model. And if I were to graph all 25 of those lines on the map, I would kind of get this kind of random stuff going on, and then they would kind of close in on a band of performance. Then I have model B, and I make some change to the model, something that I hope is going to change its behavior, improve it, or make it operate differently, or something. And the same thing happens there. I run model B 25 replications, and it gives me some numbers. And they kind of start out kind of all like this. And then maybe it finally settles down, and then we have something like this. Now, the width of my chalk line here is the variance of my answer. That is, the more variance there is in the answer that's coming out of the simulation model, the more variance there is in the measure, the wider this line is, the less certainty I have about what that measure really is coming out of the simulation. It's clearly a difficult problem if the variance of the two answers is so great that they overlap each other. If the two answers have so much variance that they overlap each other, I can't actually claim that one of them is different than the other. I need to see a distinct gap between the answers that is wider, that there's a gap between the answers that's wider than the joint variance of those two answers. So I need to reduce the variance. I need to have variance reduction. And there are a lot of things we can do to accomplish variance reduction. They're beyond the discussion in this class. But one of the key things in variance reduction is making sure that we have consistent random numbers in the inputs to the model. If we can separate the random numbers and keep the random number uses for each activity distinctly separate so they don't mix in with each other, we will get some variance reduction right there. Then there are other things we can do. All these advanced mathematics where you can measure the outputs of the models and measure the inputs of the models and do some correlation checking between the inputs and the outputs, and then reduce the variance that way by doing some kind of correlation stuff with the results. But random number streams are a big part of this, keeping control. Because if you don't know what your inputs are, then clearly your output has more variance. You have to have more range in the output because you didn't even know what you put in the beginning. So clearly your numbers coming out are going to be more loose, more unknown. And then someone said to me, well, that's all fine and good, but why don't we just run the models longer and this problem will go away? Well, what if this is model A and this is model B, and they're giving me a result where they kind of do this natural cyclic pattern, and there clearly is something going on where I don't know if this is the answer or if this is the answer, because they keep doing this thing. Running the model longer doesn't solve my problem because the pattern just keeps doing its rhythmic cycle, its weather cycle. What could be doing this kind of cycle? Well, what if I'm simulating customer demand over a period of years, or weekly demand even? Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday has a pattern. Has a pattern to it. So we're going to see a pattern in the customer demand, in the passenger demand for the transit system. Doing it longer, if these two guys keep cycling like this, isn't going to give my answer any better. The answer is not going to change by running the simulation model longer. The answer is going to stay the same. So this doesn't solve the problem. Running the model longer doesn't cure the issues with bad model design or bad random number sources for the model. Questions?
Can solution not be where you have the top of, for example, A, and when you have the top, then you make the normal variation? I don't know what it's called in English.
Well, the solution would be, first of all, to try to verify that these curves are correct. So the question in this example was, well, are these curves this way because the random numbers made them this way? Do these curves really represent the model performance, or do these curves represent some kind of fluky artifact of the random number stream? If these are true, if these curves are genuine and really are what the performance should be, then okay, fine. Now we got to work with it, and we got to interpret these curves and say, well, we're gonna figure out how to compare these somehow. We're going to either separate them out by the seasons and compare them and create a decision variable, an input parameter where we look at to compare these according to what part of the curve that we're on, and maybe only do comparisons at the peaks of the curves or something. We're gonna do something with that. But if these are the result of the random number streams, and we think our model's perfect, but we're getting this result because our random number streams are all goofy, then running the model longer may give us a different answer and make us feel like we did a better job, but it's not a better job. So this idea that if I just run the model longer, all my mistakes will go away, it doesn't work that way. They don't go away. They can actually get worse. You fundamentally have to have good model design, and you have to have defensible model design that maintains a separation between control and alternative. Hypothesis, null hypothesis, and alternative hypothesis have to be clearly defined. And in the simulation model, they have to be clearly defined, and they have to be clearly drawing the correct input streams of data so that you're doing the correct experimental comparison between the two. So we went through this before coffee break. I want to emphasize over and over again, random number generation is very important. Reduction of variance, stream configuration in your random number, in your simulation model is extremely important for reduction of variance. Just want to keep pounding that into your head because that's so important, and you should never forget that if you find yourself in the position of writing your own simulation model for something. But now we've done that and have a little bit of fun. Just spend the last 20 minutes or so of class, and I can walk you through. I'm going to sit down again. I'm going to walk you through some models that I have built over the years for railway purposes. Let me close this model. Nope. And go over here and over here. And let's start with this one first. And let's do, how about this one? So what is this model doing? So this model, I'm going to get up and draw on the board what I'm talking about here. So this model was for, this goes way back. This model is 12 years old. I did this 12 years ago as a student project. I got an honorable mention award for it. And what I'm looking at is a railway line carrying passengers. I have stations. Basically, I have 10 stations or so. One, two, three. That's close enough. All right. And I want to calculate if the train itself has is going down the track and it has some kind of delay factor, whatever, how does that impact the passengers riding on the train? And what should I do? I'm going to assume that the train's delays are out of my control. The train's delays are there. They're random. They're going to happen. I'm not even going to have a conversation about changing the train's delays. That's just a fact of life I have to deal with. What promise do I make to the customer? What promise do I make to the customer in terms of the timetable I define and how I configure that timetable to optimize the customer experience? So I define this idea for the customer of on time for the train, and then I have something that I call the threshold, which is some additional time that the train can be late, but it's still okay. The customer's not really unhappy about it. So to put this in comparison, if you're on the 150 bus coming from downtown and you're coming here, right, you know, and if it gets here 1 minute late, I don't care. Do you care? I mean, that's okay. 1 minute, it's not a problem. 1 minute late, you're really not going to be upset about that. You can just walk a little faster and make up for that. So that might be a threshold where you don't care, that's okay. Anything within that 1 minute is perfectly fine with you. And then after that, we have true delay. So I built this model, and I have the ability to set the threshold, and I have the ability to also set a buffer in the timetable. So I have a buffer for train recovery. So if the train's late, there's a buffer in the timetable to give it a chance to catch up. But then beyond that, there's a threshold that the customer will accept. On top of that is additional delay. And then below that, I measure this true delay beyond the threshold for the passengers, and I'm cumulatively measuring that. I'm measuring not on this picture, but in the actual report that gets generated when the simulation's done. I'm measuring how many passengers were delayed beyond the threshold, and what was the total average minutes of delay beyond the threshold. And I do this for a couple of different service patterns. I do this for service pattern. I have 3 different service patterns I define. One is called inbound, and that would be people getting on, people getting on, people getting on, people getting on, and the train is getting fuller and fuller and fuller and fuller and fuller, and then everybody off at the downtown station. You know, this is typical commuter pattern for North America. You know, everybody's riding the commuter line into Chicago on the Burlington route, getting on at Aurora, getting on at all these stations going in, and then everybody off at Northwestern Station downtown. And then outbound would be the opposite direction. Everybody's on, and then people get off, 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 like this. And then an inter-city model. And the inter-city model is kind of, I call it the bow tie, and it's people kind of getting on here, and then nothing changing for the first few stops because it's inter-city. You wouldn't get on inter-city just to go to the first few stations. You're going somewhere. So inter-city, and then kind of it starts to kind of randomly do like this, and then it kind of peters out at the end when people are kind of getting off at the stations closer to the end of the line. So I did this, and I was looking at this because still, even today, very often, when you look at the train timetables for a lot of services, especially in lower density services in North America, you can actually look at the timetable and you can actually see where the buffer timetable, where the slack in the timetable is. You can do this by, you look at the timetable and you actually count out the minutes between stations going one direction, and then you flip the timetable around and you count the minutes going the other direction. And suddenly you discover that, you know, in this direction it only takes 5 minutes to go between these two stations, but going that way it takes 15 minutes to go between these two stations. And there's like, well, did the track get longer going the other way, or what's going on here? And it's the buffer. It's the timetable buffer, and it's very common in Chicago, Los Angeles, San Francisco, Boston. It's very common for there to be this slack, this buffer time inserted in the last two stations of the trip, where they've got a 5 or 10 minute buffer just to keep the train on time, so that when it arrives at the station, even if it was 5 minutes late earlier in the trip, when it gets to the station, it's on time. And that's true for long distance services, and that's true for all kinds of services. So my question in this research was, does that make sense? Does that really accomplish what we're trying to accomplish? Should I put the timetable buffer all at the end of the line? Or should I split the timetable buffer up and spread it out over the trip? Should I maybe have a minute here, a minute here, a minute here, a minute here, kind of spread the buffer out over the whole trip? How would that affect the output for the passengers? How would that affect the measures in terms of number of passengers delayed and the buffer time and the total minutes of passenger delay? And for those of you that are interested, I've actually posted the report that I wrote for this model on CampusNet. You go into the readings for today's lecture, and you'll actually see the written report that I wrote 12 years ago for these models, and it explains all this stuff, and it gives you the results and the statistics and all this kind of stuff. But I don't want to go into that. I didn't really want to spend the time going through that. I want to walk through this model and give you a demonstration of the kind of complexity that you could do in a generic discrete event simulation program that's relevant to railways, right? So what do we have here? So we have up here at the top, we have this device here, which is simulating a flow of trains. So this is called a create module. And so we're going to have trains leaving at 15-minute intervals, and we're simulating a terminating solution. Terminating means, for example, very typical commuter railway line in Chicago. You know, that line might have 5 trips in the morning, and it's done. You know, there might be a trip every hour after that, but the morning rush is those 5 trips, and then service quits until lunchtime. And that's on a line being shared with freight trains. So you've got freight traffic, and then you've got these commuter traffic going on top of the freight traffic. So we're going to run these 5 trips in the morning and simulate what kind of pattern of service they give to the customers in that morning shift. And then, and this is scheduled. So these guys, this is constant time. There's no randomness here. It's just a 15-minute cycle. But then as they go down the line, they're going to experience some delay. And they're going to experience, this is the 6 minutes is the minimum travel time for that segment. And then this function right here, this refers to a function that I've calculated in another piece of the model. That's an expression, and it's going to randomly generate a delay from a random number distribution. And then this guy here is a buffer number that I've assigned for this part of the timetable. And then this guy right here is whatever the accumulated delay is up to that point, the accumulated non-corrected delay. And so here we go. This picture right here is immediately your explanation for why do I need simulation software. Because clearly this is a funky distribution that doesn't have any nice, clean textbook formula. There's no name for this. This isn't Poisson. This isn't anything. It's not even Weibull. It's not Erlang. It's not anything. It's just whatever I made up. It's something that made sense for railways. So I'm using discrete event simulation software to carefully model this very specific, kind of unique to this industry kind of pattern of delay. So I have that in that box, and that repeats, that same structure repeats itself for each block, each track block down the line, with obviously with the labeling changing for each block, buffer 2 and buffer 3 and buffer 4, et cetera, et cetera. So I have a distinct, unique buffer for each track block. And I won't demo it. I don't think I want to demo it right just now. But what I did with this is there's another piece of software that goes with Arena that can run this simulation model and tune these buffers automatically. I can give it parameters, and I can say, you are allowed to adjust the buffers within this range. And it can actually run this simulation hundreds and hundreds and hundreds of times and keep tuning those buffers until it sees the buffers fall into a range that are going to give the best result for the output parameters that I specify, which in this case were passenger delay. And so it's going down the line here, and I'm managing the semaphore conditions. I've got a block here that's acting as a semaphore. It's a hold, it's a queue hold kind of block, but it essentially prevents a train from entering this block until the semaphore is cleared, and the semaphore gets cleared when the train leaves the block, and I set the semaphore token to 0. So someone else asked me in the middle of the coffee break, you know, can I do all the kind of stuff I want to do in railway modeling in a package like this? The answer is yes, if you're willing to spend enough time doing it. This was perfect because it is designed to answer a specific question that I had to answer. There obviously is a point where you get to a level of complexity where it trades over and you want to say, well, I'm going to spend the money and license some kind of commercial package that's already developed, that already does all these specific things I need to do, like Berkeley Rail Traffic Controller or OpenTrack or something like that. But for something where you're trying to answer a more focused, narrow question, you would definitely go to a generic simulation tool and just develop the model yourself and build it. So anyway, so we can run this model. And my icon is not a train, unfortunately. I didn't have a library of pictures suitable for that. But it's going to float these in. It's going to float these trains through the model and simulate their delay. And in the model right now, the buffer is 2 minutes at the last station. And this is inbound intercity, so there's 200 passengers getting off at the last station. We just run that model. I can fast forward it. And there we go. So I have custom generated output report things here for what was the train delay. This is the measure of the train delay. And then I have a measure of how many passengers were delayed. And then what was the delay time for those passengers. And if you look at the report I posted online on CampusNet, you can see how the balance between count of passengers and quantity of delay shifts as we start tweaking the parameters of how the timetable is generated. And you see this kind of shift where at some point it looks like they're really far apart, but as I change the parameters and change the way we perform, they get closer together in terms of count versus total minutes of delay. So that's one example of early work I did in Arena for railway stuff. And the other one I did is more recent. I got a little bold and thought I would try my hand at a contest, so I did one of these hump yard simulation contests. This guy's a little bit messier. This guy's a little bigger. This represents about 200 hours of programming, maybe more. And let me just get this. There we go. Let me close this over here. Do that. There we go. Missing my scroll bar at the bottom here. There we go. So what do we have here is, bless you. We have a hump yard. We have a hump yard model. And in the simulation model, I'm modeling incoming trains. And then I have a loop here. I have a resource, a hump yard engine, that is grabbing these trains and dragging them up to the hump and pushing them over the hump. And then the hump is splitting the train car by car into its destinations. And each one of these lines is a separate track in the hump yard, and the cars are riding up over the hump and riding, and these are the queues. These queues are emulating the track, storing the cars in the queue. They're being held in that queue until way over here, there's another engine that does a little loop, and it goes to the hump yard, and it picks a train to pull from the hump yard, a set of coaches or railway freight cars, drags it out, and pushes that line of cars into a departure track where it's going to get ready for an engine and go. And then once it's done doing that, it loops around and does that over again. And what we're interested in this model is essentially, what should the decision rule be for which train do I take out of the receiving yard and hump first? And then which one of these tracks do I pull first? So it's a two-stage decision. Which train gets humped first? Which pile of cars in the sorted tracks in the bowl gets pulled next into the departure yard to go? And within the parameters of the contest last year, the decision pretty much came down to we should always pick shortest processing time first. That we should always pick the shortest train first and send it up over the yard and get it going. So I can run this model. Oops. And once again, I didn't have any pretty train graphics, so I had to use the built-in. So we're filling these classification tracks, and then they're getting pulled. And I'm recording data at various steps along the way, tracking statistics in my report outlines. And then I'm departing the trains. This is how many departure tracks are busy at any one time. This is the train size, departure train size. How big a pull I'm doing from the yard. This loop is managing the resource of the pull engine that's doing the pull out of the bowl. And this is tallying the number of cars that are accumulating in the bowl. And the numbers grow and grow and grow, and then the track gets pulled. So we can fast forward this. And it's actually quite a long simulation, but it's still reasonably. So I've got it set to run. I should have set it for a shorter run time, but you can see what's going. Actually, if I come up here and shorten this up. There we go. So here we go. And so we can do all these kinds of measures. Oh, I didn't do, there we go. I only did one replication, so none of these averages are going to have a number. I only have the minimum, maximum value. These are actually the numbers from the one replication right here. But you can see I've got all these measures of utilization and busyness. But you can do all this. You can develop your own custom models to solve custom problems. And very often, a lot of these managerial decisions in railways require this kind of custom development, because you can't just go buy a software package that does hump yard simulation off the shelf. And the problem keeps changing over time as they change the technology and the requirements of the yard. So that about finishes up our conversation for today. We've covered discrete event simulation and queuing theory, and we've seen the importance of reduction of variance in the real world and controlling for variance in our modeling of the real world, controlling for how we model our discrete simulations, controlling how we do random number generation, and controlling how we separate the model structure so that we don't create artificial variance in our answers coming out of the simulation software that distorts the answer we're trying to find in the models that we're building in the first place. And then I've shown you some examples of what we're able to do with generic simulation software to model real-world situations. What we have coming up next, we have a break. We have a week break. And then the week after that, we have a long series of field visits, so you won't be listening to me talk very much here for the next month. We come back from break, and we are going to Roskilde the week after break. And stay tuned. I'll send out a notice with clarity on meeting details and things like that. But you will be traveling from here to Roskilde, and hopefully you can make it. We can accept late arrivals, but ideally you would get there on time. It would require leaving campus before noon to get there on time, because like an hour and 15 from here to there. And the meeting's time starts at 1 o'clock in Roskilde. So, and then the week after that, we are going to the Metro, Copenhagen Metro, down there. And then that brings us up to November 4, and so your case studies are due November 4. And then November 11, we go to DSB Dispatch. And then November 18th, we do timetabling at the DSB. We have a presentation at the DSB on timetabling. So we have a long series of, we're not going to be in this classroom again, basically, except once after the break. So a lot of field visits. And then we'll tie things up at the end of the semester. After that, we'll have probably a kind of a project, kind of in-class project. I'll probably bring in a track diagram. We'll probably play around with modeling that track diagram and doing some CPLEX and doing some timetable construction for a real-world track diagram. I'll probably get something from Jutland or something like that, and we'll get a piece of track and actually model how the trains move on that track and then build a timetable for that track. And then it'll be end of the course. We'll be done. Any questions? No? Stay dry. It's a little rainy and blustery out there, and have a great day.